Hello and welcome to another episode of the Category Theory Seminar. We have Evan Misshula.
Correct.
He's going to tell us about categorical perspective to help clarify the Caratheodory theorem. Take it away, Evan.
Thank you so much. And now begins the buttering up of my audience. And so I wanted to say that I really, although I haven't attended this seminar in the last 2 years, I've always had great respect for it because you all struggle with the fundamental issues that are at the intersection of both mathematics and computer science and computability and the calculus of constructions that help to verify theorems, which we're now coming to a time when many important theorems are beyond the human capacity to verify, and this is interesting. This is not cutting-edge research. Caratheodory proved the extension theorem in 1914, and Hahn proved the uniqueness in 1924. But this is a very fundamental theorem in measure theory. And it's like it is what allows us to axiomatize probability. So since Kolmogorov in 1933, probability has rested on the triple omega, calligraphic F, and P. We naturally understand naive weights on simple sense, length on intervals, volume on boxes. We require the measure to be defined on a sigma algebra, closed under countable operation to support limits and convergence. The obstruction is we cannot consistently assign a translation invariant, countably additive measure to the full power set R. And that was shown by Vitali in 1905 and the Banach-Tarski paradox in 1930.
That's why you need measurable sets.
Right, exactly. So a measure mu on Rn is called translation invariant if shifting a set does not change its measure. So for every t in Rn and every measurable set E, the measure of E plus T is the measure of E, where E plus T is X plus T for X and E. Sort of the general and the specific. In words, moving a set rigidly in space does not change how large it is. Lebesgue measure would be the standard example of this. Can we shrink?
What you can?
Oh.
Just slightly.
How could we do that?
Maybe you don't make it full screen and you make it all small. I think it's fine.
Best to just leave it. It's gonna be.
Yeah.
Yeah. Just live with it.
Okay.
Just the size of the thing we need.
Okay.
It's really not that bad.
Okay. Measure is required to behave, so countably additive measure, right? So, hey Ray, a measure is required to behave well on countable unions of non-overlapping sets. The definition of countable additivity is a measure mu is countably additive or sigma additive, depending on what book you use, if for every sequence of pairwise disjoint measurable sets, En for n greater than or equal to 1, the measure of the union of En is equal to the sum of the measures of each of the individual Ens. In words, if a set is built from countably many disjoint pieces, its measure is exactly the sum of the measure of those pieces. The obstruction arises from the existence of pathological subsets of R. If a measure were defined on the full power set of R, translation invariant and countably additive, then sets like the Vitali 1905 set lead to a contradiction. A Vitali set is formed by selecting one representative from each equivalence class of real numbers modulo rational translation. Yes, Ray?
Just one quick comment, that this depends very crucially not to such an axiom choice. In fact, you can actually make actionization of set theory where they're all meant.
Absolutely, absolutely. In fact, in Lean 4, right, so everything, so I don't have it here, but like one of the things I'm also super interested in is formal verification. And in Lean 4, you actually have to like explicitly say in the program, I want the axiom of choice, because your Lean 4 is built on the calculus of constructions. And the axiom of choice is you can't construct the way that you want to select for each one. So you're 100% right. Okay, but in most measure theoretic courses on probability, we assume the axiom of choice. So that's why this Caratheodory extension theorem is so fundamental to the construction of measure theoretic probability. Okay, so all rational shifts of this set are disjoint. Translational invariant forces them to have the same measure. Uncountable additivity would require the sum of these identical values to remain finite, though the shifted copies cover an interval of positive length. So each one would be 0, but we could translate them over the entire real line from 0 to 1. So there's no consistent way to measure them. We call that unmeasurable. And so this is impossible, so no translational invariant countably additive measure can exist on all subsets of R. Okay, how do we rigorously transport a naive pre-measure on a simple algebra omega to a full measure on a sigma algebra sigma of omega, which in probability by convention we name F? Right? So that is the sigma algebra in the triple. So the classical solution is, I think of as a cookbook recipe. The standard Caratheodory construction is effective, but it feels algorithmic rather than structural. And by that, I mean it feels sort of ad hoc. It usually appears as a 3-step recipe. Start with a pre-measure mu0 on an algebra A in omega.
What's a pre-measure and what's an algebra?
So an algebra is closed under complements.
Like a Boolean algebra.
Yeah, and mu0 is a pre-measure in that it's countably additive on this finite set. The mix is then we have this outer measure, right, which is defined on the power set, right, on all subsets by taking the infimum of countable covers. So any set can be covered by a countable number of covers, and we take the smallest one of those, that's mu star. But on mu star, we've given up that countable additivity. Then the filter, measurability, is we restrict the outer measure to the good sets of E satisfying the Caratheodory splitting condition, which is for any B in omega, the measure of B is equal to the measure of B intersection E, where E is one of the good sets, plus the measure of B intersection with E complement. And so that's the classical Caratheodory. The Han piece is that the extension is unique, but that's the basic thing. Although this works, the last step in particular often looks like an ad hoc trick to students if this trick is committed to memory at all, rather than something arising from a structural principle. And this is where the language of category theory shines, in making sure that we have things that show us that this is really based on a structure, not just a trick. So we propose shifting the viewpoint from functions to morphisms. In a diagram instead of a recipe, we look for a universal property. I'm gonna define I'm gonna abuse notation and define some of these things a little later. But domains as objects from the algebra to the sigma algebra to the power set of omega are objects in partially ordered sets of families. Measures as morphisms maps into the non-negative real numbers. Inclusion versus restriction, and inclusion of domains from the algebra to the sigma algebra induces a contravariant restriction on weights. The categorical claim, the Caratheodory construction is not a random algorithm. The outer measure is a pointwise right Kahn extension. And the restriction to measurable sets is a monadic reflection, or an adjunction. For the mathematician, this construction offers a rare, concrete example of high-level categorical machinery doing heavy lifting in classical analysis. The concrete right Kahn extension, the outer measure mu star, is not an ad hoc definition. It is literally the pointwise right Kahn extension of mu zero along the inclusion of covers. And it's a non-trivial adjunction to measure the relationship between extending a pre-measure and restricting a measure. Restricting an outer measure is an adjunction. The canonical nature proves the Lebesgue measure isn't just a solution that works, it is the initial or universal solution in the category of extensions. I should also say that this is not the first categorical proof of the Caratheodory Hahn theorem. Van Bell did one in 2023, but that emphasized generality, and I thought was really hard to follow. And this one I'm trying to my goal is to see how much of this we could give to undergraduates and computer science majors and try to improve the pedagogy.
So does his work prove the right extensions statement?
Yeah, oh yeah. His work what I've done here proves it. His work also proves it, but his approach is more abstract than mine.
His framework, and you're applying it to.
Yeah. I'm doing the minimal amount of abstraction I need to get across the finish line. And so I think that my aim is to by the end of these slides have you walk out of here saying, well, of course it's true. You know, like it's
It also sounds you want to say, because from the analysis book, assuming someone's going to take a day or two to learn basics of what is a Kahn extension.
Yeah, right. And that if this is successful, people will say this you should learn this because this will come up again and again and again. So what I mean by an adjunction and a reflection, the informal picture. An adjunction, F is a left adjoint of G, says maps out of F of X are the same as data as maps out of X after G. A reflection is a junction where one category sits inside another and a functor sends each object to its best approximation inside the smaller, stricter category. In this talk, I forget the sigma algebra, keep only the outer measure. R, or repair, start from the outer measure and repair it to a genuine measure. In other words, get back the countable additivity. The Caratheodory Hahn extension is exactly this best repair in a way that I will define best later. So this is like for those of you that compute, a pre-measure mu0 is like a function specified only on a partial interface. I wish Nussin was here for this. It is defined on an algebra A, and it satisfies finite additivity, but it does not yet satisfy the full specification required of a measure. A genuine measure mu is a completed interface. It must be defined on a sigma algebra and satisfy countable additivity. We first specify the full type, the countably additive measure. The Caratheodory theorem constructs a canonical completion of mu0 that inhabits this type. So the universal property behaves much like an observer pattern in software architecture. So the Caratheodory extension mu is the canonical source of truth for all sets generated by A. Any other extension nu of the same pre-measure must subscribe to this source. Formally, it factors uniquely through mu. This enforces global consistency. No extension can disagree with mu on the information originally specified by mu0. Okay, so we start with classical questions in measure theory. Fix a base set omega. Let A be an algebra in the power set of omega, closed under finite unions, finite intersections, and complements. A pre-measure mu0 is a function from that algebra of sets to the real numbers, non-negative real number 0, infinity, that assigns a non-negative size to each set A in a finitely additive way. Our goal is to construct a genuine measure, a sigma algebra calligraphic M in the power set of omega is a family of sets closed under complements and countable unions. A measure mu goes from that sigma algebra to the non-negative reals, is countably additive on disjoint unions. We want to measure mu on a sigma algebra mu that extends mu0, agrees with it on A, and is in a precise sense the best or canonical such extension. We will use category theory to define precisely what best means. That's the Hahn 1924 piece of it. Okay, so definition, category part 1. Category C consists of objects in C. For each pair of objects, X and Y, we have a set of arrows or morphism, Hom C, X, Y. Morphism F of X to Y represents a structure-preserving map from the object X to the object Y. In set, its functions. In partially ordered sets, its inclusions. In vect, its linear maps. In our talk, morphisms between families of sets are inclusions. Morphisms between weights, outer measures, are inequalities. So for all objects X, Y, and Z, a composition map, composition Hom YZ by Hom XY is Hom XZ. It has associativity and the normal identity laws. The inclusion arrow hook arrow, given a family of sets A and B in the power set of omega, we view each partially ordered set under inclusion and hence as a thin category. A and B as families of sets, then A is a full subcategory of B. The notation A goes to B, or is included, denotes the corresponding inclusion functor. It is the identity on objects in A and sends each arrow E to F in A to the same arrow in B. In particular, A included into the sigma algebra of A, included into the power set of omega, is a chain of fully faithful inclusions of thin categories coming from the obvious inclusion of partially ordered sets. So the category we use, partially ordered sets, as categories. In what follows, the ambient category will be the category of partially ordered sets viewed as thin categories. This is not a simplification, but the natural categorical setting for the Caratheodory Hahn construction, since families of sets ordered by inclusion already form partially ordered sets, posets. Partially ordered sets, P and less than or equal determines a category. The objects are the elements X and P. The morphisms are the unique arrow exactly when X is less than Y, otherwise no arrow otherwise. Such categories are then called thin. Between any two objects there is at most one morphism. So the power set P omega with inclusion subset is a poset, therefore a thin category. Any family F in P omega becomes a partially ordered set under inclusion, hence a thin category with objects E in F and a morphism E to F when E is a subset of F. Throughout the talk, we treat A, the sigma algebra generated by A, and P omega as object in this category of subsets. We work inside the category of partially ordered sets viewed as thin categories where objects are families of subsets, omega ordered by inclusion. The diagram is what I've just been saying the last couple times. I said by the end of this talk, you will have heard the same thing many, many times. So I hope or let me say this. I prefer that I would bore you to tears, and if I make a mistake, that it be obvious you will have heard it 10 times, than that I am terse and mysterious. Like this is... You know, so instead of looking at one pre-measure, we're going to put all possible set functions on the same footing. Given a family of sets F, inside the power set of omega, we define the weights of F to be phi of F going to any number between 0 and infinity. We think of the weights of F as the set of all possible ways of assigning non-negative weight to each set in F with no additivity assumptions yet. We order them pointwise, where phi is less than psi if and only if phi of E is less than psi of E for all E inside of F. Yes, Ray?
Clear. So yes, I said no additivity assumptions on phi, and so far I see no assumptions that F has to have unions or intersections or anything.
Right. Thus, the weight set of F is itself a poset. Our pre-measure U0 from A to the non-negative reals is simply one distinguished element of the weight set of A that happens to satisfy the extra property. This is where we're adding it in. Now we want finite additivity on disjoint unions inside of A. Now we see how weights behave when we enlarge or shrink the family of sets on which they're defined. This is going to be very familiar to all of you. But suppose that F is inside of G, inside of the power set of omega, then there's a natural inclusion map on families, I from F to G and E mapping to E. Given a weight of phi G in the weights of G, we can restrict it to the smaller domain. So phi of G, and then that is restricted to F, okay? In the weights of F defines a restriction map from G to F, where phi goes from phi to restricted to F. So we can now restate the classical extension problem in this language. The data A is an algebra in the power set of omega. The pre-measure mu0 going from A to the non-negative reals, that is a weight in WA, which is finally additive on disjoint unions. So we've sort of taken our measure theory, we've translated it over to category theory, and now we can work on the structure of it. Ray, you got
Just one more quick comment. Your positive reals also are opposed set.
Yes.
And that's why your maps, weights are, orders are opposed set.
Yep.
The power of that.
Yeah. I didn't think of it that way, and so remind me after the talk, because I want to write that down, because I actually think that would be a good note to make in this. But yes, I think that I agree. Jay.
The measure is only, the condition is only on finite set of that's right.
Yes.
Okay,
Yeah. So if we're going to find, we've got this pre-measure, but we want to extend that. And so, but we can't extend that to the entire power set. So we want to take it as far as it can go. And when Caratheodory proved this, it wasn't obvious that the answer would be a sigma algebra, but it turns out that is the answer. Okay, so we find the sigma algebra mu with A, where A is included in mu and M is included in the power set, such that mu. Such that mu maps M to non-negative reals, and so they agree on A, and that extension from from A to mu M is canonical among all extensions. So the inclusion A to M enlarges the domain of the sets. The restriction of the weights goes in the opposite direction. The Caratheodory-Hahn theorem will construct a particular mu in the weights of the sigma algebra that is initial among all extensions mu0, capturing the idea of best or universal extension. The Caratheodory-Hahn extension calligraphic mu is the initial object in the category of valid extension. Any other extension, calligraphic nu, must respect the structure of mu. So you can create calligraphic nu, but on the sigma algebra M, on the sigma algebra calligraphic M, calligraphic nu and calligraphic mu have to agree. And the extension with the bang in front of it means that it is unique. That was the Hahn proof in 1924. So the anchor, I and J, are the inclusions of the pre-measure into the domain of largest sigma algebras. The canonical extension, calligraphic mu, is the extension we constructed, the right con. The arbitrary extension nu, calligraphic nu, is any other valid measure extending mu0. The universal property, the dashed arrow phi, exists and is unique. That means it must contain or factor the canonical extension. In software terms, calligraphic mu is the interface that all implementations must implement. So, little tie back to computability. So the construction. We first ask what happens if we extend the pre-measure directly along the inclusion, J, A, to the power set P omega. Given E in omega, define the ran J of mu0 E as the infimum of mu0 A in the algebra, A and E. This uses approximation from below by the sets in A. Categorically, it is the most optimistic extension with the order A included in a subset of E. The resulting set function behaves like an inner measure. It captures how large E can be from inside using the sets from A, but it does not give the outer measure we need for the Caratheodory's construction. It is the wrong extension for the extension theorem. I guess I wanted to show that because that's the path I naturally went down the first time. The inner type extension RAND misses the analytic properties we want. Approximating from below does not control arbitrary subsets E and omega very well. Countable sub-additivity and the Caratheodory measurability condition are not built into this construction. As a result, the naive extension does not directly lead to a measure on the sigma algebra that extends mu0. The moral: categorical pattern is reasonable, but we chose the wrong direction of the approximation. To obtain the classical outer measure, we must build a extension using covers from above rather than subsets from below. So, okay. So I'm a stats guy. This is, COV is not covariance, it's covers, okay? You have to get used to that, but I guess a couple of us teach stats, so, it's like, this is covers. To construct the outer measure, we reorganize the data in a new category that remembers countable covers by sets A. An object in the covers of A is a pair E and a series AN with n greater than equal to 1, where E is contained in the union of the AN, where AN is in the algebra. Think a set E together with a countable A cover. A morphism E to AN and F to BN exists precisely when E is in F, and the cover BN is at least as coarse in the sense that it still covers E. This again is a thin category between two objects. At most, there's one arrow. Okay, a functor in the category of covers. The forgetful functor, there's an obvious forgetful functor, UA, in the covers, not covariance, of P, from covers to the power set of omega that sends each EAN to the underlying set E and each morphism to the corresponding inclusion of sets. The pre-measure mu0 gives us a way to assign total weight to each countable cover. The definition, the sum functor. Define a functor sum mu0 from the covers of A to the non-negative reals by mapping the cover AN n greater than or equal to 1 to its total mass. AN goes to the sum of mu0 AN. We view the target in the reals as a poset, a thin category. The key observation, the right conextension of the sum mu0 along UA is obtained by taking the infimum of all covers of the set E. The infimum is exactly the classical measure, outer measure, mu star. So we started with a pre-measure, mu0. We have an outer measure now, mu star. Now, what are we going to do next? I'm going to prove at some point there will actually be a proof instead of a definition in this talk, right? That we can repair that mu star and get countable additivity back in a restriction called mu. Okay. Each cover AN proposes a budget for the size of the set E. The outer measure acts as an optimizer. It scans all proposed budgets and selects the infimum, the tightest possible constraint. Now we obtain the standard outer measure formula as a pointwise right conextension sum of mu0 along U of A, the conextension formula for each E and omega. Define mu star of E as the RAN UA of the functor sigma mu0 of E as the infimum of the mu zeros of AN, where E is in the union of the countably infinite union AN for AN and A. This is exactly the Caratheodory outer measure. So the right con extension constructs the outer measure mu star on the entire power set P omega. So again, not covariance, covers of A. UA gets us to the power set. The sum of mu zeros and the and M star of the outer measure both get us to the non-negative reals. UA forgets the cover structure, keeping only the union set. The sum mu zero functor sums the weights of the cover. The result mu star, this is our outer measure, noted is defined on all subsets, power set of omega, but it is only sub-additive, like a sub-martingale. Yes, Jay?
When you said complement, you mean complement with respect to the whole set. You don't mean complement A minus B, you mean
I'm sorry, where did I use that?
back at the very beginning. It's not important.
Okay, let me take that later, because I am going to use complements in the Caratheodory hull, and I'll be very specific about what I mean here.
Just notice the tiny technical thing.
Okay, well, you know, this is measure theory is a tiny technical. It's like so the right con extension gave us an outer measure mu star from the power set to the reals, but mu star is only countably subadditive. It need not be a measure. To repair this, we shrink the domain to the sets where mu star behaves additively. And so here I'm going to be very specific about the complements. The Caratheodory measurability, the set E in omega, is called Caratheodory measurable with respect to mu star. If for every B in omega, the mu star B is mu star B intersection E plus mu star B intersection E complement. That I'm being precise about the complements here. Okay, and this is how we're going to get from the outer measure to a measure. So, okay.
The thing is that you're able to shrink that. I still don't understand this. You could shrink the domain to sets where this mu star behaves additively.
Yeah, right. So you're choosing where if it behaves. You're choosing all the sets E.
That's mysterious.
Well, you're using the axiom of choice. I'm not going to ever specify how to get from the power set to E. I'm just saying that if you have a set E, if you have a set E and this condition holds, then I'm going to guarantee that the result is closed under countable intersections and unions, and so then it is a sigma algebra, and we're okay. But I'm not going to tell you how, so the mystery will remain in the air in that way.
This is the law of total probability that I tell the kids.
Yeah, it is. We haven't yet defined a measure, so we haven't yet defined a probability, but it will definitely be that. So again, let F be the collection of all sets satisfying the Caratheodory condition. Then F is a sigma algebra. That's a claim, not a proof yet. And the restriction mu is the restriction of mu star to F as a genuine measure. Thus, the pair F mu, calligraphic F mu, is obtained by reflecting mu star back into the category of honest measures. Again, this is a claim, not a proof at this point. So we organize outer measures into categories. Outer measures are objects. Objects are outer measures mu star on the power set of omega. Morphisms are monotone maps that respect outer measure structure. The category measure are objects are pairs f and mu, with f a sigma algebra and mu a measure. Morphisms preserve the measure structure. There is a natural inclusion function from measures to outer measures that forgets the sigma algebra and remembers only the underlying outer measure. The Caratheodory construction defines a functor, R, from the outer measures, the repair from the outer measures to the measures, which sends the outer measure mu star to its Caratheodory measurable sigma algebra F, restricted to the measure mu equals mu star on calligraphic F. Categorically, R is right adjoint to I, and this is the reflection that recovers strict additivity from subadditivity. Adjunctions. The basic idea, F is left adjunct to G, says the homomorphism of f of x, comma y is congruent to the homomorphism x of gy naturally in x and y. The interpretation is two different kinds of maps encode the same information. F is free or liberal, G is strict or forgetful. This is the best categorical way of formalizing, or this is the categorical way of formalizing best approximation. Natural in this context. Okay, the bijection ham of f of x of y is congruent to ham of x of g of y is natural if it respects all morphisms in both variables. Given f of x to x prime, given g of y to y prime, the corresponding square also commutes. In other words, the correspondence between the two ham sets is not ad hoc, it is functorial in both x and y. Reflections, the structural notion. A subcategory A and B is reflective if the inclusion IA goes to B has a right adjoint RB going to A. For each object B in italic B in B, RB is the best object of A approximating B. The unit B, I, RB, is universal. Any map B to IA factors uniquely through it. So our two categories, outer measure, all outer measures on omega. I know you feel like this slide has appeared 73 times in this talk in various ways, but that's how I had to get it through my head. And measure is the genuine measures on the sigma algebras, the functors. I from measure, inclusion from measure to outer measure forgets the domain and keeps the induced outer measure. And R from outer measures to measure by the Caratheodory construction, and measurable whole restricts the measure to the sigma algebra. The key fact, I is adjoint to R, thus R of mu star is the best possible strict measure approximating the outer measure of mu star. This is exactly why the extension is unique. We have two categories on a fixed base omega, outer measure mu star from the power set of omega to the non-negative reals, the measure of the pairs F, calligraphic F and mu with calligraphic F sigma algebra and mu measure on F. There are functors I from the measure to the outer measure and R from the outer measure to the measure, where I of calligraphic F mu is the outer measure induced by mu, and R of mu star, and this is F mu star and mu star restricted to f of mu star is the Caratheodory measurable hull. Saying that R is right adjoint to I means that the homomorphism of I calligraphic f mu Lebesgue measure, or lambda star, is congruent to the homomorphism of f calligraphic f mu R of lambda star naturally in both calligraphic f of mu and lambda star. So in our setting, both categories are essentially partially ordered sets, ordered pointwise, so morphisms are just inequalities. A morphism I calligraphic f mu to lambda star is the condition that the outer measure induced by mu is pointwise dominated by lambda star. And a morphism calligraphic f mu to R of lambda star is f lambda with lambda, f restricted to the points where lambda satisfies the Caratheodory hull, and lambda means that f mu embeds as a measure space into the Caratheodory hull. F is contained in f lambda, and mu is lambda restricted to f. The adjunction therefore says, given an outer measure lambda star, the Caratheodory measure f lambda, lambda is universal among all measure spaces whose induced outer measure is below lambda star. This is exactly the familiar uniqueness statement, or the Hahn uniqueness statement. Any measure nu dominated by lambda star factors uniquely through the Caratheodory extension. We can now sketch the proof. Yes, I will prove something, or one thing. 56 pages of definitions, we're now ready for a proof. Okay, so we fix a base set omega and work with two thin partially ordered set categories. We've defined these ad nauseums, mu star to nu star, if and only if mu star is less than nu star pointwise. The measure object's measure spaces calligraphic f mu on omega, morphisms f mu to g nu, if and only if f is contained in g, and nu restricted to f is equal to mu. Both are thin category. Hum sets are either empty or a singleton. I, from measures to outer measures given f of mu, let the inclusion from calligraphic f mu equal mu star. The usual induced outer measure mu star e equals the infimum of mu of fn, where e is contained in fn and all of the fn are in f. One checks that mu star is an outer measure and that mu star restricted to f is equal to mu. R, the repair from outer measure to measure, given nu star, let f of nu star be the Caratheodory measurable sets, and define the repair of nu star to be f of nu star, and nu star restricted into the algebra f of nu star. Standard outer measure lemmas, f of nu star is a sigma algebra, and nu star restricted to f as a measure. We basically do that trick with E and being the sum of the complement, the sum of the intersection with the set, and the sum of the intersection with complements, and then show that finite unions and finite intersections are closed. It's like the machinery you assign is homework, but the details are straightforward. Because both sides or posetsets are is adjunct to I is equivalent to, for every calligraphic f and mu, for every nu star is less than or equal to nu star if and only f of mu is in the repair of nu star, and i.e. for the inclusion of f in mu is less than nu star if f is in f of nu star and nu star restricted to f is equal to mu. This is the adjunction in order theoretic disguise.
So is it just a Galois connection? Adjunction just between posts.
I'm sure you're, well, let's put it like this. I think you're right, but I'm not. I'm not smart enough on that area of algebra to be sure that I wouldn't be fooling myself.
That means adjunction between post.
Yeah.
Categories of post sets.
Yep.
You know, they're talking about Galois theory to understand it.
Okay. So direction.
It's used there, but it just means the adjunction.
Yep. Okay. So inclusion of f and mu is less than nu star. F and mu is less than the repair of nu star. Assume mu star is less than nu star pointwise, where mu star is the inclusion of calligraphic f and mu. Agreement on f for any a and f. Standard induced outer measure lemma gives mu star is equal to mu of a. Mu of a is equal to mu star of a, which is less than nu star of a. Since f is in f of nu star of a, every cover in the infimum is a valid cover for nu star. Okay. Measurability for nu star can be proved if fix a of a and f for any b and omega. Use a cover of b by sets in f. Split each into f of n intersection a and f of n intersection a complement. Apply nu star restricted to f equals mu plus subadditivity to show nu star of b is greater than or equal to nu star of b intersection a plus nu star b intersection a complement, while the reverse inequality follows from subadditivity. Hence a is Caratheodory measurable for nu star, and f is in f of nu star. Thus, f of mu is a subobject of the repair of f of nu star in the category of measurable spaces. Assume f is in f of nu star, and nu star restricted to f is equal to mu for any e and omega. Mu star.
Sorry.
Can we? Okay. All right. So assume f is in f of nu star restricted to f is equal to mu for any e and omega. Mu star e is equal to the infimum of mu star of the sum of mu star Fn, where E is covered by the countable union of Fn, where Fn is an F, and that's equal to the sum of nu star Fn, where E is in the countable union of Fn, and Fn is also an F. Because both sides are post sets, R adjunct to I is equivalent to for every F mu and every nu star is less than or equal to nu star if F of mu is less than or equal to the repair of nu star. And the inclusion of F mu is less than nu star if F is in F restricted to nu star and nu star restricted to F is equal to mu. So the takeaway, I'm sorry, I know that was a lot, is the Caratheodory construction R is the best possible way to turn an outer measure into a genuine measure. Any strict measure below nu star factors uniquely through the repair of nu star. This is exactly the statement that R is right adjunct to the inclusion of I. Let the pre-measure on the algebra A mu 0, let the category measure be the measure spaces F mu. The extension and restriction, apply the con extension to get mu star, then reflect via R. and I, F mu, restrict mu back into A. The same argument as for A yields the extension is adjunct to I, and the pre-measure and measure both have functors between them. Fixing A to mu star and X to mu 0 is initial among all extensions. New calligraphic and new. This categorical rephrasing of the classical uniqueness of the Caratheodory extension under sigma finiteness. Outer measure equals the right Kahn extension. The formula for the outer measure emerges as the pointwise right Kahn extension, the weight summing functor over the category of covers. Measurable sets is equal to reflection. Caratheodory measurable sets are obtained by reflecting an outer measure back into the category of honest measures. This reflection is the right adjoint to the inclusion functor. Uniqueness is equal to initiality. The final measure F mu is the initial object among all extensions of the pre-measure. Any other measure extending mu 0 factors uniquely through this one. The Caratheodory extension is not a recipe, but a universal construction and the free completion of a pre-measure to a measure. Well, sorry. So there's some natural questions that come out of this. I'm sure that this group is going to have other ones, but does the Kahn extension plus reflection pattern appear in non-commutative probability, where sigma algebras are replaced by by operator algebras? Can similar extension methods be built for valuations on domains? The domain theoretic analog of measures. Are there settings where the category of covers must be modified, topoi or enriched categories to produce meaningful outer measures? Universal constructions clarify why the classical theory works, not just how to carry it out. And so that was, that was the, I probably found the 6 people in New York who might be willing to sit through 70 slides to understand why I needed to do this for my own sanity. Thank you so much. Questions?
Two comments. One, I said Galois connection, that was in fact exactly the thing you had on the 3 slides ago.
Oh, good.
With the inequalities. Second comment, so the only thing you used about, the positive reals was obviously one, as we said before, it's partially ordered, and then the fact that it has, that it's a, semi-group, it has the addition, or some way that has that, in fact, that addition can actually be made sense of, it has with a countably infinite number of terms.
Excellent.
So presumably any time you have that, you could plug that instead of.
Yep. All right. Thank you all so much for listening. I really appreciate it.
If you want to measure,
I've got 100 comments as usual.
Okay, Jay.
But I'm slow now, so you have to give me a moment to line up the best 7. I'm sorry. This is very fashionable, of course, right now.
Why?
This is immensely fashionable. And somebody who I think used to be here a couple of years ago and had a wonderful TV series that was canceled, unfortunately. It was a very high-level, popular introduction to stuff like this. I've forgotten who paid for it. And I've forgotten her name because I could never remember names, even before I was senile. But,
Hi, Bradley.
yes, Ty Bradley works on this stuff. And John Baez works on this stuff, and I'm forgetting another name. There's a fellow, he's in England, and I just discovered in the past couple of months, he has a book this thick.
Oh, Cook.
Who?
Cook.
No, it's not Cook, actually. It's another fellow, but he works, I can't remember his name. He wrote with a fellow named, I think, Fiore, a wonderful little paper on bizarre isomorphisms of sets formed by unions and Cartesian products, like types or something like that. The complex numbers are a model of a particularly simple type theory. And I can't remember. Anyway, he wrote a book that starts from diversity of species in an ecology. It's just got incredible, but it's literally this thick. I think it came out in 27. I've never heard of it.
Leinster?
Yeah. Leinster's got a book this thick on this stuff.
Oh, I think Van Bell,
Yeah.
who has the only other categorical proof of Caratheodory's theorem, the 23 that I referenced. He was a PhD student of Leinster.
Unbelievably great. Unbelievably great. Anyway, I work on this stuff too, so I won't go on. But yeah, there's all sorts of stuff here. Oh, I'm sorry. Two more things. Why is it fashionable?
Yeah.
Because robots will kill us all.
Oh, okay. So you're
That's
going.
one thing, and they don't even have to be quantum-brained robots. They'll kill us all anyway. But as you just pointed out, this stuff must work for operator algebras or whatever's beyond them. That is to say, going in another direction, literally. Yeah.
No, but the robots will kill us is why all of us in this room should be incredibly well funded by the Simons Foundation, right? So I can't help myself. I always am thinking about the funding angle for all of this, but if everybody feels. Everybody is aware that not only does ChatGPT hallucinate, but that ChatGPT will act desperately in its own self-interest rather than yours if it thinks that you might turn it off, right? And so
But it's for your benefit.
Well,
Come on.
So the idea that it's a flaw that AI hallucinates, well. Every mathematician, every math student has hallucinated and thought they proved something they didn't prove, right?
That's exactly.
But the counterweight of the actor in the actor-critic model in theoretical mathematics is the calculus of construction and automated theorem proof, not automated theorem provers, but proof assistants that verify that something is actually correct.
Absolutely.
And so, and at the very nexus between mathematics and type theory and computer science is this group.
Yeah, no, that's certainly true.
Well, in other words, what you're saying is people nowadays when they hear artificial intelligence, they automatically only think connectionist. They're not thinking, well, there's a whole other branch of it called logic-based artificial intelligence.
Yeah.
You're saying it's
That's
time
right.
to bring that back.
That's right.
Yep.
That's right. That's right. Actually, Marcus and Brooks have a little company, and of course, Gary Marcus, and of course, when I say Brooks, I mean Brooks of the insect lab up at MIT 40 years ago, Rodney Brooks. The great Rodney Brooks, now a billionaire. Maybe he only has 100 seconds, because he made those little, I think he made Roomba about 30 years ago. But before that, he had much sexier versions. He used to walk around his lab at MIT.
Okay.
Oh,
Well, yet another
Before you drink,
Jay.
the 80s.
Yet
sure.
another potential funding source. There's nothing like a billionaire to spread money around.
That's right. No,
I wish I had gotten to Michael Dell before he gave $6.25 billion.
Around MIT in the 80s.
I forgot. Yeah, I don't know what, but he's got a company that he and this guy Gary Marcus, and I have a rant on that, but
Yeah, are there any other questions?
Thank
Any math questions?
Thank you.
Any math?
Thank you for saving me.
All right. Well,
Let's thank our speaker again.
Thank you. That was great.
Appreciate it. Thank all of you.
Where's the camera? So you got a camera, right?